Hello. I think we're live, so welcome if you've just joined or you're just logging in now. I can see we've got some people viewing already. We're going to look at proof today. So we've got a maths home study club session again. So Mondays and Wednesdays, we've been running these for maths. Welcome to everyone that's joined, and perhaps you've been before. Thanks to those that have been already and taking part in the chat. Has been a real kind of crucial part to this. Hello, welcome. Hope we're keeping well. Obviously, we've got loads of stuff planned for the coming sort of weeks and days in terms of sessions on YouTube. This one today is on proof. So we're going to start sharing the screen shortly. Feel free, as usual, to comment, ask any questions as we go. I believe one of my colleagues has dropped a link as well to the PowerPoint we're going to be following. So feel free to look at the slides ahead of time or alongside me now as that's been dropped into the chat. So welcome. Right, I'm going to share my screen with you. So do let me know that you can see it. So let's share the PowerPoint. So we're going to look at proof today. Can we all see that? Is that clear? Hopefully that's appeared on your screen now. Excellent. And I'm just going to make that full screen. So we're going to look at proof as a topic, which is a big one for A-level. It's kind of, there's some new bits to the A-level since it changed in 2017. And proof is a big topic that there's now a bit more emphasis on. So proof is covered a little bit in year 12 in terms of the kind of very much algebraic proof, which we're going to have a little look at today. There's also the idea of proof by contradiction, which is a big A-level topic. This is a new part of the A-level. I didn't see this until I went to university and did my undergrad in maths. Until I started doing maths at university, I didn't really see proof by contradiction. So proof by contradiction appears in the A-level now, and I've recently done a session on this on Snap Revise, but we're going to look at proof in general today. Welcome, excellent. Glad to see people joining. Lovely. So this is very much AS A-level in general. So this will largely be focused on year 12 content, yes. So the AS more typically that kind of proof. But as I said, contradiction is a bit of proof that we do in year 13, and we'll get to that towards the end as well. Okay, so in general, this is very much proof. Hello, welcome if you're just joining as well. I've just shared the slides, so hopefully you can see and hear that all nice and clearly, and we'll get started. So feel free to work alongside me or ahead of time if you're feeling confident with this. Proof is seen a little bit at GCSE as well now, but very much just algebraic proof and a little bit of disproof as well. So let's go, let's have a little look. And feel free in the chat to message any answers as well. Right, the other thing to remind you is that towards the end, there'll be a discount for Snap Revise, a code that will expire soon, so you need to pay attention to that. But here we go. Right, first question, state whether the following statements are true, false, and if false, provide a counterexample. This feeds into the idea of proof and disproof that we see at A-level. And we need to be really clear on what these words mean as well. So feel free to ask if you need anything clarified. I'm happy to take time now to just really make sure that this is clear. If A is rational and B is rational, then A plus B is rational. So we just want a true or false. So please feel free to submit your thoughts on these. If A is rational, good, right, let's clarify what rational means because this is really kind of crucial. Rational means it can be written as a fraction. So I'm just going to make that clear. Rational means can be written as a fraction, means we can write it as a fraction. And this is really important that we understand that word because that comes into a lot of proof that we're going to do. So means we can write it as a fraction, and excellent, a simplified fraction even. So we can write it as a fraction. And I know that you're thinking about one of the proofs by contradiction specifically there. So that's really good to see. So rational means we can write it as a fraction. And that would be, so some people confuse this because they think, okay, it can't have an infinite amount of decimal places, but a third is rational. and that is 0.3 recurring. So recurring decimals do count as rational numbers. Something that would be irrational would be something like pi or e, or something that we need to introduce a new symbol for it. It needs its own Greek letter, or it needs some sort of symbol or sign to denote it exactly. We can't write it as a fraction. So for example, the square root of 2 is an infinite decimal that's changing, and we can't write it as a fraction. So rational means a whole number or a fraction. I can write it as a fraction, worst case scenario. Excellent. Yeah, I thought so. Brilliant. Good. So some of this stuff might be familiar to some people here, which is wonderful. What do we reckon for the first one? If A is rational, meaning it can be written as a fraction, worst case scenario, and B is rational, then A plus B is rational. So think of sometimes it helps to think of some examples. Hello, welcome. Do think about numbers to try out, and then think generally, okay, would this always work? So these are really just one mark, little quick questions. Will that always be true? And we can try some out in our head and then think, okay, in general, will this be the case? So let me just move that out. So what do we reckon? Excellent. Right. First one is absolutely true. Yeah, true. That first one would be true. If the first one's a rational number and I add another rational number to it, I'm going to have another rational number. There's nothing that's going to make it irrational when I do addition. Is that clear? Do feel free to ask if not. So a rational plus a rational is another rational number. It might be that they're actually whole numbers. That would still be considered rational. Cool. And then the second one, second part, what do we reckon here? If A is rational and B is irrational, then A plus B is irrational. Let's have a think and pick some numbers if you're not sure. So what do we think here? Right, and good question, really good question coming in. Would we have to prove that? This is very much a, is it true or false? So anything of this sort of standard where we're just either choosing an example or a counterexample is normally a little one marker question. So that was a really good point someone's raised there in the chat. And this could be year 12, some of this stuff, some of the proof we're going to do today, particularly the algebraic, but it is very much a feed into what we're going to look at in year 13. So more likely you're going to have harder proof questions in year 13, but it's pretty good for year 12 and 13 to be going over these ideas. Lovely. Okay, so we reckon for 2 that it's true. I agree with that. Well done, if that's what you said for that one. So excellent, and a nice suggestion there, choosing half and pi. There's no way that that's going to be a nice number either. Okay, so if you add an irrational to a rational, there's still, to express it exactly, it's going to be irrational. Okay, the irrational bit doesn't tidy up. Okay, so very good. Good. Okay, that is a point. And that's more going on to what we're going to look at for contradiction. We have got to be careful that when it says prove, we have to do it in general. And this question hasn't asked us to prove, it's just asked us whether it's true or not. Okay, so it's a very watered down kind of question. It's not proof. If we want to disprove something, we only need one counterexample. So very well done if that's kind of the question you're getting at. To disprove something, you just have to find something that doesn't work. But to prove it, you can't just pick one number. That's absolutely right. You have to have an understanding that in general, it will always be true. And that's really what we're going to move on to look at today. So very good questions coming in. Part 3 then. This is absolutely applicable to all exam boards. So as I've mentioned before, there are topics that we're trying to focus on in these sessions that since the new A-level in 2017, there's been stuff added to all of the A-level as a whole. So every exam board has had to follow it quite strictly, really. So yes, this is applicable to all boards. This one is actually false. Yeah, can anyone think of a counterexample whereby this wouldn't work? So if A is irrational and B is irrational, that when you add them, it wouldn't be irrational, it would be rational. Any scenarios? Strange, because this feels like it should be true. A good try there, because there is an underlying relationship with E and the natural log, but that would be more to do with sort of composite functions, that one. 0.6 That's a lovely example. Yeah, 2/3 plus 1/3. Hang on. We've got to be careful there though, because 0.6 recurring is rational. So a good try is that would prove that kind of a rational and a rational, that would be an example, would still equal a rational. We need to think of two irrational numbers that when you add them, they make something that's rational, because we're suggesting this is false. Anyone think? Because thirds and 2/3 don't count. They are rational. Okay, so we've got to be really careful here. So think of some irrational numbers we know, maybe pi. Right. If I take, for example, pi, and I take another irrational number, such as minus pi, that's made something rational. And I know maybe we don't like 0, but it would still count. It would still count as a rational number. Does this make sense? So I've added two irrationals here, and they've cancelled each other out to make 0. And a lot of the time when we look, when we look for counterexamples, and I've said this before in sessions, the way we can get round it, they're normally only 1-mark questions. You've got to look at these almost obvious but easy to miss ideas. Zeros, ones, can I make 0? Can I make 1? Could I times by 1? You've got to really carefully think, there's probably a very specific case for which this won't work. Can I think of it? And it's normally one of those that we miss or forget about. Exactly. It is a little bit cheeky, that one, but good, very good. So we'll move on, because this was just 3 marks and we just had to get it sort of bang on. Let's keep going. So very good. So we'll have a look at this one together firstly. I think I might be blocking the question a bit here, so I'll read it out for you all. Let me see. Right, complete each of the following by putting the best connecting symbol in the box. Explain your choice, giving full reasons. And we've got this double-headed arrow, which means if and only if, it's true kind of either way. And we've got 2 kind of implication arrows. And I, again, didn't really get to use these logic symbols until university. And they actually appear, if you do philosophy or you do anything with logic arguments, you see these symbols all the time, and they're really important that we get them the right way round, because not always, if something implies something else, it's not always true the other way. So this one here means if and only if, meaning it works both ways. If that's true, that's true. If that's true, that's true, vice versa. Whereas sometimes there's a directed way that something implies something else. So let's do this very carefully. And again, the slides have been copied in. If you would like to look at these and you're quite confident you want to move ahead even, that's fine. So if we've got n cubed plus 3 is an odd integer, n is an even integer, we want to work out which way round it's in, what implies what, or if they're both always true. Okay, any suggestions here with how we could think about this? Right, and I like how we're putting this in the chat, because this is a bit strange when you haven't got the symbols. It is a bit tricky. Excellent. Right, we'll have a little look now, because it's easy for these to get it the wrong way round and it still makes sense to you, but you've just drawn it the wrong way or whatever. So what we've got is, if n is an even integer, so let's think about this as a kind of, if we talked it through, if n was an even integer, we know that n cubed is even as well. Okay, and then n cubed plus 1 would, as a result, be odd. So hopefully that, going from there to there, going from this side to this side, makes sense. Let's just be careful the other way round, because it might feel like, okay, so that'd be the same true backwards. And a lot of the times that could be the case. However, remember, if there's any scenario where that isn't true, it doesn't imply it. So we need to be very cautious. Now, if we think about n cubed plus 1 is odd, and see if that's true the other way, then n cubed is even. Okay, but if I cube root it, so say for example 3 was my n cubed plus 1, and then n cubed was equal to 2 when I took 1 away, the cube root of 2 is not an even integer. And what is an integer? And that's some part of the question we could easily miss. Okay, there are scenarios perhaps where it's not an integer. An integer means what? Does anyone know what recognize that word? A whole number, absolutely. So we can't guarantee, because if I chose 3 as n cubed plus 1, which I can, because if I'm saying can I imply it this way, and I took 1 away and cube rooted, it wouldn't always be an even whole number. Okay, so that's where we need to be careful, because we can't guarantee that if n cubed plus 1 is an odd number, that when you minus 1 and cube root it, it will definitely be an even whole number. Okay, so this is only an arrow that's going this way. Well done if you got that, but tricky. Very easy to do this part and then say straight away, well, that has to work both ways, because we've got to be so careful checking it both directions. Is that clear? Is that clear so far? Even if to begin with, you kind of thought, I suspect it's both ways. Does that make sense that the right-hand side is sort of implying the left? The statement on the right implies the first bit. Okay, hopefully that's clear, but feel free to let me know if not. So this one, we've got x minus 3, x minus 2 is greater than 0, and x is greater than 3. Okay, so if x is greater than 3, we can do a similar argument here. Then x is greater than 3, then that's bigger than 3, and that would be bigger than 3 as well. So two numbers, sorry, that's positive, so that will be bigger than 0. Okay, but if we try it the other way round and we assume this is true, it doesn't tell us x is always greater than 3. So again, this is this way round. It's only an implication that direction. A really good question there. So if there's one counterexample, you can't write the double-headed arrow. Absolutely, and that's what we were showing in the first one. If there's one counterexample for both ways, you can't write anything. There's no implication at all. It could be that these two statements don't relate in any way. That's the other thing we haven't considered. This question was suggesting that it will be one of those three. But that's absolutely right. If there's any counterexamples at all, what we need to be cautious of is we can't say that this will always imply this. So absolutely, and that's what we noticed for the first one. It didn't work the other way because there was a counterexample, or maybe loads of counterexamples. So good question there. Just to repeat part 2 then. So for part 2, if I just do that over here, what we found was that if x is bigger than 3, x is greater than 3, then what we know is x minus 3 would be bigger than 0, because I'm taking away 3 from something that's bigger than it. So if that's bigger than 0, and then I do x minus 2 would also be bigger than 0. So the product of two things bigger than 0, two positive numbers, would be bigger than 0. So that absolutely works for this implying this. If x is bigger than 3, this product will definitely be bigger than 0. Is that bit clear? And I do agree, I needed to recap that because I kind of rushed the second bit. Is that part clear? So if x is bigger than 3, it does imply the other one. However, if we look at the other way round, and I look at the scenario of the product being, yeah, super. But if I now say, right, I'm looking at this case, does this imply the other way round? Right, so I'm saying this is definitely bigger than 0. If x is 0, then what we'd have is minus 3 times minus 2, which is greater than 0 because it would be positive 6. So here's your counterexample. If you did two negatives that times together and make a product bigger than 0, that doesn't then imply that x is bigger than 3. So what I'm basically saying for the other way round counterexample is these could both be negative and still make a product of something that's positive. And so that the left could be greater than 0, but it wouldn't imply the other way round. Is that clear? I think that's the harder one to maybe get your head around. This again is only true this way. This implication only works this way round. So if you take a value for x where these are both negative, you get a positive product bigger than 0, but the right-hand side then won't be true. Brilliant, okay. Well, it won't be greater than 3. This is what we're checking. We're checking if that product is bigger than 0. Does that mean x will have to be greater than 3? And absolutely, it doesn't mean that. So that's why we can't put the double-headed arrow. Brilliant. Good. Right, I'm going to move on. So this one here, this notation might not be familiar to everyone. This is something we see in year 13. Does anyone know what these symbols mean? What this? You might have seen it in stats, you might have seen it, not in stats, you might have seen it in mechanics, you might have seen it in pure. It's a bit of a strange time, obviously, with schools, because a lot of schools do start the year 13 content at the end of year 12, but the way things are at the moment, everyone's all at different places. That means identically equal to, brilliant. So that means all values would be true. So excellent, that is an identically equal to symbol. And the signs like that are absolutely, they're called the modulus signs. So they mean you take the positive version. So what we're saying here is if I have a plus b and I do the modulus of that, so even if they were negative numbers, I make it positive, is that identically equal to the modulus of each of them added up? So just to give you a quick example, if you've never seen that symbol before, right, where we've probably seen that sign is to mean the magnitude or the size of something in maybe like a vector form. You might have seen it as the modulus, meaning do Pythagoras and get the actual length. That's fine, but it also has got this element of being positive. So we can't have any negatives. It makes it a scalar magnitude quantity as opposed to having any negative symbol associated. So that's probably the bit we haven't necessarily seen before. So as an example, -3, the modulus of -3 is 3. I only care about how big it is in terms of the magnitude. I don't care about plus or minus. So essentially what it does is it makes any negative positive and any positive just stays positive. So it just turns everything positive. So what this is saying is show by counterexample that that statement is false, that any number plus another number modulus is always identically equal to the modulus of the two separate ones added up. Can anyone suggest numbers? Right, we've got a few suggested there. Let's have a little look. So we've got to be careful here because some things will work. Some things actually, if I add them and I make it positive, or I make them positive separately and add them, it still gives the same value. So we have to pick one specifically that doesn't work. And it is a bit tricky actually. So there are, when you first try it out, things might look like they work, but we do have to be careful. But don't worry either way, because I don't actually think this is that obvious. I think we have to be really careful here. So I would suggest you can still do this quite algebraically. -5 and -5, let's have a little look. So good, I think that would work actually. Let's have a look. Almost. -5 and -5 would, I think, work. But if you took the positive version, then we'd have an issue. So for example there, if you have -5 and +5, okay, that is not equal to -5. Oh, I'm writing 15 here. That is not the same as that. So -5 and +5, the modulus of that would be 0. And that is not equal to 5 plus 5. Okay. So basically, in general, what we can say is if we let A equal -B, if we let them be the opposite signs of each other, when you add them up, they're going to cancel to 0 on the left-hand bit. But when you modulus them separately, you're going to get double the first thing. You're going to get 2A. So that's where we need to be really careful, because what we'd end up having is A plus B would cancel out, whereas A plus modulus of B, which is really -A, modulus -A equals 2 lots of A, and that's not equal to 0. So does that make sense? Right, good question there. Is it trial and error? For a lot of these disprove counterexample questions, yes, it's try some numbers out. But as I said earlier, And these are really good points you're making, guys, because we need to tease this kind of stuff out. What I kind of mentioned earlier is that actually they're still normally very low mark questions. So you have got to be careful that you don't overspend time on it. And my biggest bit of advice is you try a few numbers out and you go, okay, 7 and 8, no, that doesn't work. -7 and -8, no, that doesn't work. And then you've got to start thinking, what are going to be the weird cases? When there's a 0, when there's a 1, how can I change it to make it a little bit bizarre? Could I consider 0? Could I consider 1? Could I consider something irrational? So you have to pick things that are going to give you the weird, quirky cases, because other numbers that are similar probably give similar results. So absolutely, it is essentially a little bit of trial and error, but you have there's ways that you can kind of still develop exam technique for this, which is what I'm getting at. So you don't want to overspend time on it. If you're thinking, this is taking me ages, you're probably almost overcomplicating it. You've got to find that weird scenario. Okay, but the more you do of these, you'll see it's quite simple. Pi and minus pi. Yeah, absolutely. Of course you could. Pi and minus pi. It didn't say anything about rational or irrational. And actually, if one is the negative of the other, it will disprove it for this case. So the easier way is just use letters, use A is minus B. But if you want to pick an actual value, pi and minus pi is absolutely fine. Yeah. Yes. So some of these disproof questions, counterexamples, there might even be infinitely many different answers, but you only need one. Okay. By counterexample, you only need one to disprove something. So that would get you the marks. You wouldn't get more marks for showing more counterexamples. If you do it properly, and you do it with one, and you just, I would say for 2 marks, plug it in explicitly and show that doesn't equal that, you'll get both marks. You don't need to do more because there's 2 marks there. Okay, so in general, anything disproof or counterexample based, you just need one counterexample and that does disprove it. Good, excellent questions, guys. And the chat has been brilliant today because it's great to see how you're thinking through these, especially if this is quite a new topic to you. So this one is a little bit weird. Show by counterexample that the statement cos theta equals cos phi that implies would tell us that sine theta equals sine phi. So you actually need a bit of understanding about these trig functions, how they look and how they behave. Any suggestions here? So this question is telling us that this is false. This isn't always true. There's a counterexample. Can you find it? And it's actually very similar lines of thinking to what we just did. So any suggestions here? Any way we could think about this one? And again, no problem with picking some values in your head or on your calculator, typing them in and verifying to yourself that doesn't work. So that would be an okay example to use or counter example to use. So absolutely try some values out and prove that that doesn't imply that. Okay, any suggestions in the chat? Any ones that we could use here? And again, think along the same lines as the previous slide. So they've just used a different Greek symbol. Okay, they could have called it A and B or X and Y or X and Z or something. Yeah, any numbers. So that again, if that Greek is confusing you, it's just algebra. It's just like calling it A and B. Right, so we're thinking about maybe what the functions are doing, which is brilliant. And this is very easy to throw us off. So what I would suggest, if you think about the sine graph and the cos graph, I'm going to draw this very roughly. So there's sine is kind of doing that, isn't it? Different angles. And obviously you might not have done radians, you might have only worked in degrees. And cos is doing this. Kind of trying to do this as best as I can freehand. So they are different functions. And I'm going to stop there because it's not brilliant. But basically what we're saying is if the cos value is equal to another cos value, does that imply sine of that same value gives the same output of sine of the other value? So the way I could best describe this, okay, cool. So we're thinking at maybe key points here. And again, I'm going to show you in general and we can choose some specific numbers. If, for example, you might notice with the cos graph, if I remove the sine graph for a minute, are we happy that whatever cos does, it's mirrored in the y-axis? So cos of 30 is the same as cos of minus 30. Is that clear? So if, for example, a bit like the previous question, if theta was equal to the minus version of phi, then what we'd have is that would work. That statement would work because cos of the value is equal to the negative of it. So you might be thinking of the 180 thing, that's fine, but this hopefully makes sense. If you chose 45 degrees and then you chose cos of minus 45 degrees, they would give the same output value. Okay, so that's kind of important. But if you plug that in sine, you plug that in the sine function, it won't generally work. Because what we'd have here is this would be true. Cos theta would equal cos phi, because cos of minus phi is equal to cos of phi. So that would be fine, but it would not work for theta. So if you chose 30 and minus 30, that doesn't work in sine because it comes out as the negative. Because for sine, what we have is we have sine of the angle is equal to minus sine. That's what would be happening there. Any questions? Exactly. Yeah, that's a good example. So if you choose a number, you'll notice that if you choose the negative version, a bit like this previous question here, where we chose a and minus b, what you'll notice that happens for cos is it does give the same output because they've got that symmetry around the axis. However, if you put that value in sine, it doesn't have the same symmetry. It gives you the minus version overall of the answer. So a totally different output. We're not trying to, good question, we're not trying to show that these equal signs are false. We're trying to show that this statement does not imply this statement. So if we have cos of something equals cos of a different number, which can happen because it repeats infinitely, we're trying to say that it won't be true for sure that sine of that angle is definitely equal to sine of the other angle. So for example, if you chose 30 and minus 30, this condition would be satisfied. But that does not imply that sine of 30 equals sine of minus 30, because it doesn't. Does that answer the question? So basically, any value, again, like the previous question, where you pick the negative version of the angles. So what we're doing for counterexamples, I see where the confusions may be coming in. You're picking values for theta and phi here to show that this doesn't work. So we're trying to show that in general, this statement does not mean that this statement is true. Certainly, there could be values of angles where sine of it equals sine of something else, but they're not the same angles that would work for cos, is what we're trying to show. I chose it to be a negative version. You might have found different values that work as well, because it's an infinitely repeating function. There are other values that would work as well. If you're looking at other values of cos that are equal, that's absolutely fine. But because of that symmetry, I think it's a good, easy one to see for cos, that they'd have the same output, but that wouldn't work for sine. But of course, again, there's many different answers you could have here. So very good, excellent questions, guys. And hi, welcome if you've joined as well. We're going to keep going with these because we're getting on to some really good points with this as we go. Right, prove or disprove, here we go, the following statement. Now, I would also, don't know if they're given there, look for the marks, because remember, as I said before, if there's a low number of marks, it's probably a disproof. There's probably an easy way of showing something. Now, this says, welcome if you're just joining. No, no cube of an integer has 2 in its units digits. So I would probably suggest, I mean, I haven't seen many questions like this, but they could ask it. If there's a suggestion that you could disprove something, remember we only need one counterexample. So I would probably start by just looking for a counterexample. So no cube of an integer has 2 in its units digits. So we're going to look for, is there a cube number that ends in 2? So get your calculator. I don't know my cube numbers that well. Probably get up to 5 or 6. But after that, it is a little bit tricky. So have a little look, get your calculator out and see if you can find any. And I'm going to keep checking in the chat as well. Any examples there? Suggest them if you've got one. Some people have got it. Excellent. It's done. Brilliant. Right. So just checking, guys, can you all still hear okay? Yeah, super. And 6 cubed, what did we get for 6 cubed? Yeah, super, brilliant. Okay, cool. So any counterexample disproves it. That's it. You've done it. Super, well done. Great. So as soon as you've got one, you've disproved it, you can move on. So let's move that on shortly now. Okay. Right. I think laptop's getting a bit warm. So if you can hear a sort of fan, I think that's probably the laptop. But let's keep going because we're doing really well here. Very good. Right. A little bit more involved this one. Please have a go at trying to multiply this out and see what we get, and then hence prove it's divisible by 8. So this is a very much an algebraic one. Let's give this a try. And feel free to, brilliant. Feel free to share that in the chat if you've got it. I know it can be a bit tricky to type sometimes. Thanks, guys, and excellent work as usual today. This is brilliant. Right, okay, so let's be careful here. So part I, timesing this out, what we're going to get is we are going to get, so we're going to get 3 to the n squared minus 1, because like a difference of 2 squares, the middle bit's going to cancel. Excellent. And you can write that as 3 to the 2n minus 1. Super. Well done. So what we can do is hence prove that if that is a positive integer, then this is divisible by 8. And there's two kind of weird ways we could do this. So I kind of want to go through both of them. So here, let's have a little look. So first way we can do this is if it's a positive integer, let's take a couple of scenarios. So if it's a positive integer, if n is a positive integer, it's a positive whole number, then what we've got is 3 to the n would be what? Would that be odd or even in general? What do we reckon? Okay, so 3 to the n is always going to be odd. 3 to a power, if we try some out, we'll see that 3 to any whole number power would be odd, okay? But be careful here, because what that would mean is 3 to the n plus 1 is even, okay? And 3 to the n minus 1 is also even. Yeah, absolutely, good, very good point. So, but it's a power of 3, that's also what we've got to be careful with. So good, so they're even. So what we found is we've got a product of 2 even numbers. Okay, and we might think, well, that doesn't prove it. And no, at this stage, it doesn't prove it. But is everyone clear with this up to this point? That if 3 to the n is odd, 3 to the n plus 1 must be even, and 3 to the n minus 1 must be even as well, because they're 1 away from an odd. Cool. No? Okay. So if 3 to the n, whatever the power of n it is definitely going to be odd, then 3 to the n plus 1, where the plus 1 is down here, will definitely be 1 more than an odd, so it will be even. And same for minus 1. So what we've got is both of those are even, and they'll actually be consecutive even numbers. So consecutive even numbers, one must always be a multiple of 4. So you might have worked this out. Right, I'm going to return to that because there's another way you could do this question. So I could see a lot of you thinking, well, hang on, how does that have anything to do with the 2 to the n bit? I've just used the original thing I'm multiplying out. Let me just check the chat to check I'm following. Let me just have a look. Well, if you, So for powers of 3, they will be odd. When you're timesing a number by 3, in the powers, all your powers of 3 will be odd. So we have got to be careful. That's a really good point that you've asked there. So the way I'm going about proving this is proving that this is divisible by 8 by looking at the original product and looking at those numbers. But I will show you another way of doing this. So hopefully we're happy. That's even, and I times them together to get this. That's how I'm using part A. So because I've got consecutive even numbers, 1 must be a multiple of 4, because in any 2 consecutive even numbers, one of them has to be divisible by 4. So I'm doing something that's divisible by 2 by something that's divisible by 4. So what I'm doing is it must be divisible by 8. So product is divisible by 4. Okay, so then that answer is divisible by 8. But you can spell that out really kind of carefully and clearly. I'll show you another kind of algebraic way of doing this because I think this is quite hard. I don't think this is a particularly obvious one. But please do give me a general suggestion of if we followed that proof. So basically, I started by showing that that will always be odd so that I could find that both of these brackets would always be even. But on top of that, I know that because they're consecutive even numbers, one of them is a multiple of 4 and the other one is just even. So I'm doing something that's divisible by 4 times something that's divisible by 2 because originally this thing here was a product of 2 consecutive even numbers, right? So it is a little bit tricky, but what we've done is we've shown, okay, so there's 2 consecutive even numbers there. And if you do the product of 2 consecutive even numbers, because one of them would be divisible by 4, the other one's just divisible by 2, the whole thing would be divisible by 8. I'll show you another way of how we could do this, but I actually think this algebra way is a little bit tricky. So the other way we could do part 2 is we could think of sort of factorizing and stuff. So we could think of 3 to the 2n minus 1 as being equal to what it was. And if I factor out, now I don't think this is obvious, but this is a technique we do see towards the end of year 13, this weird factorizing. And this is applicable to all boards, but this is just a tricky question. So this would be challenging, I think, in general, but absolutely worth working through. Now you could factor out 3 to the n minus 1, okay, as a factor. And what we'd have in this bracket would be, this would need another 3. And this would need, I factored it out there as well. Okay, and then what I'd get is 4 times 2, which is 3 to the 2n times 8. Okay, so it's a bit harder to actually do algebraically in that sense. So I think a lot of the time the easier argument is to do it by sort of following the logical argument of consecutive even integers. Okay, so particularly this method here, because actually the algebra gets quite confusing and a little bit tricky to follow. So I would certainly suggest this method. And in terms of GCSE, this is going to be more like the one we've used in any of the smaller GCSE proofs. look at general case for odds, look at general case for evens, look at consecutive evens. So a tricky question there, but easy to deduce by a logical argument of consecutive even numbers. Okay, I think we've got another one to look at, and this is a proof by contradiction. So this is something that comes up in year 13 that is very good to kind of get ahead of and look at. So I've recently done a session on this with on Snap Revise for proof by contradiction. And it's about proving that a number is irrational. Now, the first part of the proof is done for you. So assume if we're trying to prove by contradiction that root 5 is irrational, the way we do it is we assume that it is rational. And what that tells us, for those that have seen this before, is that root 5 can be written in the form a over b, where a over b is the simplest form. Okay, this is a proof you actually basically learn almost by heart in year 13 for root 2. And then when people are asked to do it for root 5, they sort of mess it up, but it's very much the same approach. So a part of someone's answer has been given here, but we need to finish this proof off. So proof by contradiction basically means you assume the opposite and show that makes no sense. So this is probably something to anyone that's in year 12 that is very new, very unfamiliar. But it is on Edexcel as well, as it's in all the boards, but it's something you generally meet in year 13. Now, a lot of schools traditionally would actually do this topic in the summer term of year 12, because it's one of the first chapters of the year 13 content. But obviously with the way schools are at the moment, that might not be the case. So it's worth having a little run through this one. Right, so let's have a little look then. So if a squared is equal to 5b squared, so what they've done here, what they've done with the proof, they said root 5 is equal to a over b. And then they've times up by b and said root 5b equals a. And then they've squared both sides, 5b squared equals a squared. And that's how they've got to this stage. And then what they've said is a squared has a factor of 5. Because if a squared is 5 times something else, it's divisible by 5. So if a squared is a factor of 5, if a squared is divisible by 5, then a is also divisible by 5. And so we can say that a is 5 times something else. Now what we do is I sub that back in and I say 5b squared is equal to a squared, which is 5k all squared. So 5b squared equals to 25k squared. Now, if I divide both sides by 5, b squared equals to 5k squared. And so if b squared is equal to 5 times something, that now tells me that b squared is divisible by 5. Which tells me that b is divisible by 5. And this is a contradiction. And I appreciate I've gone very quickly here. If you haven't seen this before, but I'm going to just show you the general thing of the argument of how you do contradiction. And again, I never saw this till university, and I found it a real struggle to start with because it was not necessarily the obvious way round of doing it. So what I've done is I've shown b is divisible by 5, but earlier in the proof, I showed that a was divisible by 5. And in the start of the question, I said a and b was in its simplest form, and a and b had no common factors. So what I've basically shown is that this whole thing makes no sense. So root 5 can't be rational, therefore it's irrational. So by contradiction, root 5 can't be written as a fraction, and therefore it's irrational. So this was tricky, and if this is the first time you've seen it, that would have been very quick. And obviously half the proof is done for you, so it's unfamiliar. But as I said, I've done a lot of these sessions where we've gone through this very carefully on Snap Revise for proving root 2 is irrational and proving that there's an infinite amount of primes. And they're things that have been added to the A-level course now. So without it seeming sort of too daunting, the proof questions will either be quite nice in that there'll be algebraic or there'll be a disproof and so on, or there'll be one of these very set contradiction proofs that you can kind of just learn. So that's a really important point to bear in mind. So very good work today, guys. That was some really tough content and you followed that really well. And, you know, it's really tricky. But obviously, as I said, I go into a lot more depth with this in the web classes designed for these questions, and we've really targeted it to the new course. So please do bear in mind when you're looking online for resources for, you know, your course, for your A-level, for revision materials, do bear in mind that we need to be careful sometimes in that it's not always tailored to the new A-level. So on Snap Revise, if you haven't seen this before, we have web classes and you can kind of backdate and look at ones that we've done previously. And we've done ones on proof recently. We've got a schedule of ones coming up, and then we also have a drop-in. So if you do want to ask any questions or go through something in a bit more detail, we have drop-in sessions on there, and that might be worth checking out. So do head over to the Snap Revise site because there's loads of resources available. And I'm going to stop sharing that for a second. I do want to say again, very well done, because that was quite tricky today. And if I reshare my PowerPoint, so what I want to basically say is that if you have enjoyed this or you found that useful, please feel free to, you know, subscribe and make sure you watch coming up sessions on Wednesday and Mondays and Wednesdays in general for maths, because there'll be a lot of this A-level content, and we've tried to design it so that it's useful for both year 12 and 13, but more so the, you know, a lot of the year 12 content that builds into the year 13 stuff. So they're all topics that will kind of be cumulatively growing. So very well done. Thanks for the work and the kind of the comments and answers as we went there, because that was excellent on a very difficult topic. It's quite hard to type it in sometimes, so I really appreciate that. Really good. And I think the last thing to really say there is a code, again, very aptly named, that's going to expire tonight. If you do want to sign up to some of Snap Revise's resources, the things we offer, the extra tutorials, web classes, sessions, and so on, you can use that code. But do check out the YouTube sessions as well, because they'll be coming up on Wednesday, and they're happening all the time for the other subjects as well. So keep clear on what's coming up, because it might be something that's really useful for you, particularly at the moment with schools being shut. So very well done. I'm going to stop sharing that there and say thanks very much again. Keep well, guys, and thanks for that today. You worked really well with what was a difficult topic. That's brilliant. Cool, excellent. And yeah, make sure if you're interested, the discount code is there until the end of this evening. So very well done. Keep well, and hopefully speak to you all soon.